Extreme
All right. In your notes, we have 3 resistors in parallel, a 20, a 30, and a 40 ohm resistor. They're connected parallel to applied potential 120 volts. Number 1, draw the circuit. 2, calculate the equivalent resistance of the circuit, the potential drop across each resistor, and the current through each resistor. All right, why don't you give that a try?
Pause the video now.
Well, it's 120 volts, so it's probably plugged into the wall. Certainly not a battery. I don't know of a 120 volt battery. I guess there could be one. I'm sure they exist, but it seems unlikely. So we had 20 ohms, 30 ohms, and 40 ohms. All right, calculate the equivalent resistance of the circuit. For a parallel circuit, the equivalent resistance is more complicated than a series. It's 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. Keep in mind, this does not say R equivalent equals that. That's 1 over R equivalent. So if I want R equivalent, I'm going to invert this side, and I need to invert this side. So that's 1 over R1. Oops. That's not right. 1 over R1 plus 1 over R2 plus 1 over R3. Like that. All right, that's kind of complicated. Now, the way we're going to think about it in our calculators, it's going to be easiest in your calculator if you think about it like this. That this is R1 to the negative 1 plus R2 to the negative 1 plus R3 to the negative 1. We've done that. Now we got to invert the whole thing all to the negative 1. Right? So we're going to say this is 20 ohms to the negative 1 plus 30 ohms to the negative 1 plus 40 ohms to the negative 1 all to the negative 1. That will be real much easier in your calculator. And I'll show you how to do that on your TI calculators right now. All right, here I have my TI calculator simulator. And let's see how we would calculate equivalent resistance in a parallel circuit. All right, so in our problem, we wanted 1 over 20 ohms plus 1 over 30 plus 1 over 40. So what we're going to do is we're going to go 1 over 20 by going 20 x to the minus 1. So that's 1 over 20. And we're going to add to that 1 over 30, which is 30. And then we're going to go x to the minus 1. And then we're going to add to that 1 over 40, which is 40 x to the minus 1. All right. Now, we're going to add those up, and that gives us 1 over R equivalent. That is not R equivalent. That is 1 over R equivalent. So to get R equivalent, we need to invert the answer. So we're going to go x to the minus 1. And there we go. 9.23 ohms is our equivalent resistance. A 20, a 30, and a 40 ohm in parallel will give you an equivalent resistance of 9.23 ohms. Don't try and create fractions and things like that. Use the x to the minus 1 key. It's by far going to be the easiest. You just invert each of the resistances and add them up, and that's going to be your denominator. So then you just need to invert your answer to get 9.23 ohms in this case. So that's how you want to calculate parallel equivalent resistance. You want to use the x to the minus 1 key on your TI calculators. Now, in a parallel circuit, the equivalent resistance is always less than the smallest resistor, but not ridiculously small. So our smallest is 20. So I'd expect your answer to be smaller than 20, but not ridiculously small. And 9.23 fits the bill. If you got R equivalent is 0.11, that's ridiculously small. That's really small. And what you did in that case is you didn't do this last inversion. because 1 over 9.23 is 0.11. So always look at your answer. Is it smaller than the smallest in parallel, and but not ridiculously small? Make sure that that's the case. All right, so that's reasonable. Now the reason we do that is because now we can figure out the current through that voltage supply, right? Because here's our equivalent circuit. It's 9.23 ohms is the resistor, and we can figure out the current. I equals V over R, which is 120 volts divided by 9.23 ohms, which is 13 amps. I'll write it down here. So that's 13 amperes, right? We got 13 amps. So that means there's 13 amps here going through that circuit. Going through the power supply anyways, there's less current going through here, not 13 amps through here, nor here, nor here. But going through here, there is 13 amps. From here to here, it's 13 amps, and then they split off. The current splits off. So, the next question was, what's the potential drop across each resistor? Well, that's kind of easy, because they're all connected to the 120 volt supply. So 120 volts. Each one of them has 120 volts across them. All right, so the voltage across the 20 is 120 volts. The voltage across the 30 is 120 volts. Voltage across the 40 is 120 volts, right? They both are connected across, they're all connected across a potential of 120 volts. They're all connected directly to the power supply. All right, so the current should be easy enough to do. I20 equals V20 over R20, which is 120 volts, divided by 20 ohms. 12 divided by 2 sounds like 6 amps. I30 is V30 across R30. V30 is 120 volts, voltage across that one. That's a 30 ohm resistor, and I guess that's 4 amps. And the current through the 40 ohm resistor is voltage across 40 ohm divided by resistance, which is 120 volts divided by 40 ohms, which is 3 amps. All right, so it looks like we have 6 amps, and we have 4 amps, and we have 3 amps. All right, let's see, does that make sense? And we have 13 amps going through the power supply. Let's see. Well, I have 3 amps of current flowing through here, and that mates up with 4 amps. So into this junction, we have 7 amps. That means there must be 7 amps coming out. This must be 7 amps right here, right? The current in must equal the current out because it's stuff flowing. It's just charges flowing. All right, so, and then we have 7 amps coming into this junction and 6 amps. So therefore 7 and 6 is 13. We must have 13 amps flowing through here. Oh, and that's what we calculated before. Beautiful. It all makes sense. It's all coming together nicely. All right, so there we go. There's our circuit. Now, let's say I wanted to measure the current through the 30 ohm resistor. Could you slap an ammeter on there to show me where you could put your ammeter to measure the current through the 30 ohm resistor? I'd like to take a moment to do that.
Pause the video now.
All right. Well, you could have put it here, right? You could have, now you had to open up the circuit. Kind of a pain in the neck. You could have put it there, or you could have put it here. These are the only 2 places you could have put the ammeter to measure the current through the 30 ohm resistor. If you'd put it here, that was measuring the current that was going through that one plus this one, right? If you'd put it here, that measures the current going through all of them. And if you put it here or here, that would just be, or here, that would just be through the 40 ohm resistor. So there you go. There you go. There's our equivalent a resistance in parallel. All right, let's try circuit problem 1 in your notes. We had a 15 volt power supply, and we had 2 resistors in series, and we had a voltmeter, and this is 5 ohms, and this is 20 ohms. What is the reading in that voltmeter? All right, so we really need to know the current through that 5 ohm resistor. So let's find the equivalent circuit. We have an equivalent circuit of 15 volts and 1 equivalent resistance, our equivalent. And since these are in series, we're just going to add those up. Our equivalent equals R1 plus R2 equals 5 ohms plus 20 ohms, which is, of course, 25 ohms. All right, so that's 25 ohms. All right, so therefore, the current in this circuit, which is also the current in this circuit, is going to be I equals V over R equals 15 volts divided by 25 ohms. So it looks like we have 0.6 amps. So 0.6 amps flowing through there. And all right, so let's calculate the voltage across there. Voltage across the 5 equals I5 R5. What do we got? 0.6 amps times 5 ohms. Is that 3 volts? Yeah, I think that's 3 volts. Let's see. What must the voltage drop be across there then? Well, this must be, if that's 15 volts and that's 3, this must be 12. This must be a 12 volt voltage drop because they have to add up to 15. Let's see. Does that give me 0.6 amps? Let's see. I20 equals V20 over R20 equals 12 volts divided by 20 ohms. Is 12 divided by 20? Indeed, that is 0.6. It is. Because if I cut that in half, that, yes, 0.6 amps. Oh, it works nicely. Works nicely. Yep. All right. So I could have figured that voltage out 2 ways. I could have used Kirchhoff's voltage law, saying the sum of the voltage gains equals the sum of the voltage drops. Or, since I knew the current, I could have just taken 0.6 amps and multiplied by 20 ohms, and I would have got 12 volts. All right. That was circuit problem 1. Let's try circuit problem 2. Should be twice as fun. What is the reading of ammeter I3? All right. This case, we got a battery. Got a battery like that. And we have an ammeter A1. And we have another ammeter. We have a resistor. And we have another ammeter. And another resistor. And this is 2. And this is 3. And this is 35 ohms. And this is 15 ohms. All right, and we had 15 amps here. I think, because if I only knew the battery voltage, I'd be good. I think I'm going to set up an equivalent circuit to find the battery voltage, because I know the current, this is the current through the battery, right? Any current that flows through here must flow through the battery, right? It's going around like this. So the current is the same anywhere from here through to here. Now they split off, and some of the current goes through here and some goes through here, but 15 amps is going through the battery. Let's take a look at our equivalent circuit. So we got our circuit looks like this, and we got our equivalent. And if we calculate the current through here, well, we know the current through here. It's 15 amps. 15 amps is flowing through. This is the plus side. That's the negative side of the battery, because that's the long thing. So 15 amps is flowing like that. So we just need to know what our equivalent is, and we could figure out what that voltage is. Call that V bat. All right. Well, our equivalent equals 1 over R1 plus 1 over R2 equals 1 over 35 ohms plus 1 over 15 ohms. 10.5 ohms. All right, is that reasonable? Well, it's smaller than that, but it's not ridiculously small. I'll go with that. 10.5 ohms. Smaller than the smallest resistance in parallel, but not ridiculously small. All right, so therefore, V bat equals IR equals 15 amps times 10.5 ohms. Oh, that's a big old battery. That's over 150 volts. Wow, that's quite a battery. Much larger than most batteries. Wow, 157. Wow. That's a lot of voltage for a battery. All right, 157. I'm not buying that at all. Those are fake numbers, I can tell. 157.5. All right. That means that this is 157.5. 157.5 volts. Right there is that battery. That's V. All right. What do we want to know? We want to know A3. All right. I3 equals V3 over R3 equals 157.5 volts divided by 15 ohms. 10.5 amps. All right. 10.5. Let's see. Let's see if that's reasonable. Let's see. I would expect more current to go through here than here because this is a lower resistance. And these two have to add up to be 15 amps because the 15 amps goes into here and splits off into 2. All right. Well, if that's 10.5, this better be 4.5. That better be 4.5. Let's see. Let's see if it is. Let's see. I2 equals V2 over R2. All right. 157.5 volts divided by 35 ohms. Let's see. Better give me 4.5 or physics doesn't work. 4.5 amps. All right. Nice. 4.5 amps. All right. So we have 4. Oops. Wrong way. 4.5 amps going this way. 10.5 amps going that way. And they add up, they come together, and they all 15. All right, there we go. The ammeter read for A3 was 10.5 amperes. I think I'm done.